Hello, welcome to my pipeline integrity video series. My name is Colin Scott. I'm a pipeline integrity engineer based in Calgary, Alberta, up in Canada. Today I'm going to talk a little bit about fatigue length limits. A lot of us that are involved in crack management will do analyses on fatigue cracks, looking at remaining lives specifically. And I've noticed that some operators and some consultants do not use the full length of their fatigue cracks when doing their analyses. So what I'm doing here is I'm going to look into a couple of interesting aspects of the natural length limits that come into play when we're doing our fatigue crack growth rates. Specifically, I'm going to look at the natural fatigue crack length limit that was reported by Kiefner in April of 2004. This comes out of a report that was sponsored by PHMSA, and it's sometimes nicknamed the TTO5 report for Technical Task Order 5. Now, what Kiefner reported was that there was a natural fatigue crack length limit in the order of 2 times square root of dt, where d is our diameter and t is our wall thickness. I believe that there's also a crack length limit that's proposed by Ted Anderson. Unfortunately, I can't find the paper at this point, but there was one paper I recall reading that Ted Anderson had put together where he had done some finite element analyses of some failure pressure calculations, and he found that there was really a relatively short length of the crack where all the stress intensity was focused, and within his study there was sort of a natural crack length limit to be considered. Unfortunately, I can't find the paper. Once I find it, I might have to update this video presentation. We'll keep moving anyway. So let's take our fatigue crack length limit of 2 times the square root of dt and play a little game with it. If we consider the analysis of flaws using the folius factor, as we would with, say, an ASME B31G equation, we can take a look at that length in terms of the flaw length parameter Z, or Z if you're down south. When we back calculate what's going on with this particular situation, we find out that there's a natural fatigue crack length limit where the flaw length parameter is equal to 4. And if we then back calculate what folius factor that's associated with, we get a value of 1.859. Now, you probably have no idea quite where I'm heading with this if you haven't seen one of my previous videos. In one of my previous videos, I did a look at the folius factor, how it's used in ASME B31G, and how industry corrosion data matches up with the ASME B31G equation. So in order to kind of get you along my line of thinking, I think I'm going to have to backtrack a little bit and recap some of the work I've done in a previous video. Some of you might be familiar with this. If we look at some of the industry standards for assessment of localized corrosion, we'll see that there's a very common form of the equation that's used. And this was originally put together by the NG18 committee at the Battelle Institute in Ohio back in the late 1960s and early 70s. If you look at ASME B31G, API 579, BS 7910, or DNB Recommended Practice F101, you'll find a remaining strength calculation in the general form that's shown in that top equation. The remaining strength is defined as the failure strength divided by the flow strength, and that's equal to 1 minus A over T all over 1 minus 1 over folius factor times A over T. And in this case, A is the flaw depth, and T is the wall thickness. I'm assuming that many of you are familiar with that equation. In this particular case, I've not included a shape factor of 2/3 for original B31G. I've not included a 0.85 factor for the modified B31G. I have not added any factors that may be used in some of those other industry standards. But the general form of the equation stands as I've shown it. Now, if we play a little bit of mathematics, we can flip that equation on its head, flip it inside out, and we can calculate what is the folius factor for a given pipeline failure scenario. If we've done a series of experiments and we have a failure strength that's been recorded, we have a flow strength, and we have flaw depth and wall thickness, we should be able to back calculate what is an effective folius factor for that particular failure, assuming that the remaining strength calculation in the top equation is correct. Let's see if that actually works. I have found quite a bit of industry failure data. Some of it I'll refer to as the Battelle data, and that was published by the Pipeline Research Committee of the American Gas Association back in 1974. I think those of you in the business that do a lot of model validation will be familiar with that data. I also have what I'll call the Cronin data, which comes from a doctoral thesis in 2000. And then I also have a PRCI report referenced here where there is a variety of data from GL Industrial, Petrobras, the Korean Gas Company, British Gas, Nat Gas, and Transgas. Now I've compiled all of this data, and I need to be clear that I am not including any of the machined flaws. If you look at some of my previous videos, you'll see that machined flaws and natural corrosion flaws do not behave in the same way. And I believe it's very important to a study like this to separate the apples from the oranges. So there are no machined flaws. Now, if I play my little game of back calculating the effective foliage factor, I come up with something very interesting, which I think I've shown some of you before. Here we have a plot of the foliage factor on the y-axis and the flaw length parameter z on the x-axis. You'll see that I've got red diamonds that represent the data points from all of those industry data where I've back calculated the effective foliage factor from those particular failure tests. You'll also see that I've got a theoretical foliage factor shown by the red arched curve. Now the foliage factor that I've used here is from the modified ASME B31G equation. Now you'll see from the dashed line where I've put a trend line through all of the real corrosion data, we have essentially a zero slope line. And what that shows us is that the length of these corrosion failures is really not playing a major factor at all in our failure pressure calculations, even though the ASME B31G equation would report it that way. Now you're probably wondering why I've gone off on a tangent. We started off talking about fatigue crack length limits, and I've somehow done a segue here and looked at length limits, natural length limits in corrosion failure analysis. I'm going to bring these two together by showing you something interesting that we learned earlier on from the Kiefner length limit. If we look here at that calculated Z factor of 4 and we look at the foliage factor of 1.859, we can see that that foliage factor of 1.859 does actually show us an effective natural length limit in the foliage factor, and therefore by definition we're going to see an effective length limit in our flaw behavior. Now, there are two real corrosion flaws that are above that limit. One of them is over at flaw length parameter Z of 1 and shows a foliage factor close to 2. And then we also have a flaw at length parameter of 22, and that's showing a foliage factor of 2. So we do actually have two data points within this database that are over that foliage factor limit of 1.859. But in the great scheme of things, I think that this data is very, very consistent. We can see a natural length limit in the Kiefner TTO5 cracks, and we can see a natural length limit in what we're seeing in the corrosion data failure analysis from those various studies that I mentioned earlier. That's a very interesting coincidence to me. Another way that we can look at it is to plot the remaining strength against the flaw depth ratio. So here on the y-axis, we have the remaining strength, so the failure strength divided by the flow strength. And on the x-axis, we have the flaw depth ratio of the depth divided by the wall thickness. Now that red dashed line that we see is going to represent the ASME B31G equation, which would consider, hypothetically, any possible length when it comes to a failure pressure calculation. If we decide that we're going to truncate our foliage factor at 1.859, as we saw from the Kiefner fatigue crack length limit, we do actually find that it's a very reasonable bounding on all of our data points. So that gives me some confidence that there is some sort of relationship between the Kiefner fatigue crack limit and the corrosion natural length limit. That seems to be more than coincidence to me. We don't necessarily always think of cracks and corrosion going together. Corrosion, we're typically looking at flow strength failures, which implies plasticity. And in cracking, we tend to worry more about toughness. But one of the things we have to remember is that fatigue is a phenomenon that involves crack tip plasticity. So there is actually a close relationship there if we're looking at things mechanistically. So I have to ask the general question, is this a coincidence or not? Is it a coincidence that the Kiefner fatigue crack length limit is comparable to the industry corrosion data's effective length limit? I personally believe that it's more than coincidence, but I'll leave the jury out on that one to see what you think. I may be just lucky in this in looking at this data that it seems to match up, or there might be some further mechanistic explanations other than just the fact that plasticity is playing a key role in fatigue. Now, some of you know from my previous videos that I've always also spent quite a bit of time over the last 3 or 4 years in developing a new model, which I call the GEM model. And with that GEM model, which I've shown here with a green dashed line, I actually predict that there's going to be a relationship between the failure pressure of a localized corrosion flaw and the square root of the flaw depth ratio, or the square root of the remaining ligament, which is based on the flaw depth ratio. So that's shown by the green dashed line. And you'll see that this relationship is not perfect. We have, I think, 5 or 6 of our data points that are below the GEM limit. But given that there are so many data points, I'm going to consider that there's a bit of plus or minus error. And I still feel that my GEM model is worth considering, even though there are a couple of outliers here. So now I have to ask myself the question, if the Kiefner TTO5 fatigue crack length limit matches up very well with the natural length limit in the corrosion flaws, how does my GEM model come into play here? Is there any way that I can use my GEM model to come up with an equivalent fatigue length limit? Is it a coincidence that all of these 3 are very consistent with each other? So if I take a look at my GEM model and I look specifically at localized metal loss, I've published several reports where I've shown that for my model, the gamma exponent for localized metal loss is equal to the minimum of the length of the flaw divided by the ratio, but up to a maximum of 1/2. And when you wrap your head around that, you'll come to realize that that means that there's an effective length limit in the GEM model that's equal to or less than diameter divided by 4. Now we can play a little bit of math on that and say that the diameter divided by 4 is equal to 2 times the square root of dt times 1/8 times the square root of d over t. And it should become apparent in a couple of moments why I'm doing that. If we look at the Kiefner TTO5 length limit of 2 times square root of dt, we can also recast that as the length limit of diameter over 4 times 8 times the square root of t over d. Now, putting those 2 equations together and playing around with a little bit of mathematics, we can find that the length limit predicted by GEM is going to be equal to the length limit predicted by Kiefner and TTO5 if the diameter to wall thickness ratio is approximately equal to 64. Now, when we take a look at the various data that's been presented in industry, we'll see that there are a lot of diameter to wall thickness ratios in the order of 64. So that seems to be relatively consistent. Now, I will point out that if the GEM model is, I'll say, more correct than the Kiefner model, then I would predict that if we had a pipeline failure with a higher D over T ratio, higher than 64, so a very large diameter and a very thin wall thickness, that would actually predict a longer flaw length limit than 2 root dt. We might get up to, say, 3 root dt, which would go against the Kiefner limit. Unfortunately, I don't have any data to confirm this one way or the other. If anybody does know of any failures from either fatigue cracks or from corrosion flaws that are at very, very high D over T ratios, I'd certainly be interested in seeing if there was anything that could be used to look at this and confirm one way or another which one of these models is working a little bit better. So here I've given you a couple of things to think about. I started off looking at the fatigue crack length limit that was proposed by Kiefner in the TTO5 report, and I've shown from some data that length limit is actually very consistent with some data that we see in the corrosion world. All of these data points have been retrieved from public sources, so anybody is quite willing to take a look at those and see if they're seeing anything different. I find it's a very interesting coincidence, perhaps, but it gives me a lot of comfort that Kiefner was really onto something, because his fatigue crack length limit does match up very well with what we're seeing in corrosion. And as we discussed, the mechanism of fatigue is based around plasticity, which is consistent with our corrosion failure analyses. I'll also say that looking at my GEM model, I've got a slightly different approach to looking at that limit, but it does seem to be largely consistent with the work Kiefner did and the corrosion data, provided that we have a D/T ratio of up to about 60 or so. There may be some deviation if we go to higher D/T ratios, but that's yet to be determined. I haven't seen any data that may or may not confirm that. Something to think about. If you're interested in further study on this topic, I do have a series of YouTube videos that you might want to look at. Specifically relevant to this one is the pipeline integrity update to the things that make me go video part 2, which you can find. I posted that fairly recently. I do have an AMP Material Performance Magazine article which was published in August 2021 that looks at revisiting corrosion assessments for pipelines, and this recaps on some of the things we've talked about today. And I'd also like to point you towards the pipeline integrity square root remaining ligament YouTube video. That's where I discuss the mathematical or partially mechanistic reasons why I'm predicting a square root relationship with the remaining ligament. Any other videos you might like to look at can all be found relatively easily and might give you some more things to think about in the pipeline integrity world. Thank you very much for your time. If you've made it this far, I appreciate you sticking around. Hopefully I've given you a few things to think about. If you do have any questions or complaints about what I'm doing here, you can reach out to me through LinkedIn and ask some questions, or you can post comments in the YouTube video channel. Thank you very much for your time. I'll let you get back to it, and hope you have a good day. Thank you.